Hey everyone, and welcome to This Explainer. I am absolutely thrilled to guide you through today's topic because, honestly, we are taking on the most extreme, dangerous, and just mind-bending cosmic journey imaginable. We're going to explore the universe's ultimate mystery boxes, black holes. Have you ever wondered what actually goes on inside these dark titans of the cosmos? Well, today, we aren't just looking at the math from a safe distance, we're going to dive right in and experience it.
So, what really happens to you if you fall into a black hole? I want you to put yourself directly in this scenario. Imagine you're an astronaut on a deeply unfortunate yet, incredibly fascinating one-way trip. We're going to use the actual laws of astrophysics, general relativity, and orbital mechanics to map out exactly what your body and your perception of time would experience during this terrifying plunge into the dark. Just picture this for a second. You're floating in the silent vacuum of space, right on the edge of the ultimate cosmic abyss. Below you is a sphere of absolute perfect darkness, and it's surrounded by this swirling, glowing halo of superheated gas. It's beautiful for sure, but it's completely terrifying. But actually, wait, before gravity really takes hold and pulls you down into the void, I'm going to use the power of the pause button. Let's freeze you right there, hovering safely in the vacuum, just so we can actually understand the science of the monster you're about to face. Section 1, History and Gravity Basics. Humanity has actually been conceptualizing this exact threat for centuries. This wasn't just some recent sci-fi invention. Back in the 18th century, thinkers like John Michell and Pierre-Simon Laplace were already doing the math on what they called dark stars. These objects so ridiculously dense that the escape velocity would literally exceed the speed of light. Fast forward to the 20th century, and Albert Einstein's framework of general relativity gave us the mathematical proof that these things could actually exist, even if Einstein himself was kind of skeptical that they formed in reality. And now, here in the 21st century, we've gone from theory to direct observation, literally capturing images of these glowing cosmic donuts with the Event Horizon Telescope. So the absolutely crucial point is understanding how these objects wield their power. It basically comes down to three basics of gravity. First, mass creates gravity. Second, gravity bends spacetime. And third, that bent spacetime dictates how objects move. Think of it through an everyday analogy. Imagine stretching a big trampoline tight. If you roll a little marble across it, it travels in a straight line. But if you plop a heavy bowling ball right in the middle, the trampoline sags. The bowling ball is bending the fabric of the trampoline, exactly like mass bends the fabric of space. If you roll the marble now, it's going to spiral right down toward the bowling ball. A black hole is really just a bowling ball that is unimaginably heavy and infinitely dense, creating a sinkhole in spacetime that's so steep nothing can climb out. Moving on to Section 2, Types of Black Holes. Okay, so we have two main categories we really need to worry about. On one side, we have stellar black holes. These are born when a massive star completely exhausts its nuclear fuel and just collapses in on itself in a violent supernova. They are incredibly dense, but relatively small, maybe a few dozen times the mass of our sun, but all squeezed into the size of a city. On the other side, we have supermassive black holes. These are the true titans, sitting right at the centers of almost all large galaxies, including our very own Milky Way. We're talking millions or even billions of times heavier than our sun. Now, because of their sheer size, their gravitational gradient, which is how fast the gravity gets stronger as you get closer, is actually way more gradual at their edges, compared to the violent, super steep gradient of a tiny stellar black hole. Keep that in mind because it's going to dictate exactly how you, our brave hypothetical astronaut, are going to feel in just a moment. Section 3, Crossing the Event Horizon. All right, it is time to unpause our simulation. Your floating has officially come to an end, and your plunge begins. As you drift closer to the black hole, you approach the event horizon. This is it, the literal point of no return. Now, it's not a physical surface you'd bump into. Rather, it's a theoretical threshold in space. Once you slip past this invisible line, the escape velocity required to leave the black hole becomes greater than the speed of light. And since absolutely nothing in the universe can travel faster than light, your fate is permanently sealed. Once you cross this boundary, there is literally no thruster powerful enough and no radio signal strong enough to ever reach the outside universe again. This reality builds into one of the absolute most mind-bending effects in all of physics, time dilation. General relativity tells us that extreme gravity severely warps time. So we have two completely different realities happening simultaneously here. From your perspective, the faller, as you cross the event horizon, time feels completely normal. You look at your watch, it's ticking away as usual, though you might notice the universe behind you kind of seeming to speed up and visually distort. But from the observer's perspective, let's say you have a friend watching you safely from a distant spaceship, they see something entirely different. To them,
As you get closer to the event horizon, you appear to slow down. The light bouncing off of you is taking longer and longer to fight that immense gravity just to reach their eyes. So to your friend, you never actually seem to cross the line. You just appear to freeze on the edge, slowly turning red and eventually just fading away into nothingness. It's totally wild.
Section 4. The science of spaghettification.
Welcome to what astrophysicists genuinely call spaghettification. I kid you not. As you fall closer to the center of the black hole, the gravity gets stronger at a terrifyingly fast rate. This creates extreme tidal forces. What this basically means is that if you're falling feet first, the gravitational pull on your feet is significantly stronger than the pull on your head, which is, just a couple of meters further away. This massive difference in gravity acts like a giant cosmic rack. You are stretched vertically, pulled downward, while simultaneously being compressed horizontally from the sides. Think of pulling a thick piece of sticky taffy from both ends. It gets longer, thinner, and eventually, it just snaps.
So congratulations! If you fell into a stellar mass black hole long before you ever reached the center, you have officially been stretched into a giant cosmic noodle, broken completely down into a stream of subatomic particles. I know, it's a little grim, but it's such a fascinating display of pure gravitational power. Interestingly, though, if you fell into a supermassive black hole, because that gravitational gradient is smoother at the horizon, like we talked about earlier, you might actually survive the initial crossing intact, only to be spaghettified much further deep inside.
Section 5. The Singularity Mystery. So, what happens to your cosmic nodal self now? Well, you are inexorably drawn right into the singularity. This is the true heart of the black hole. Here, all the matter that has ever fallen into the black hole is crushed into a point of zero volume and infinite density. Let that sink in for a second. Infinite density. It's a concept so totally extreme that our current understanding of the universe simply cannot handle it. At the singularity, the math of general relativity just gives up. The foundational laws of known physics completely break down. Space and time as we know them literally cease to exist. As astrophysicists often note, the singularity represents the ultimate boundary of our knowledge, where the foundational laws of physics simply cease to make sense. This is the ultimate unresolved riddle for modern astrophysicists today. See, we have quantum mechanics to explain the very small, and we have general relativity to explain the very heavy. But at the singularity, something is somehow both infinitely small and infinitely heavy. The two rulebooks of our universe just totally contradict each other here, which means we are missing a massive piece of the cosmic puzzle, a unified theory of quantum gravity.
Which brings us to the ultimate question. What truly lies beyond the event horizon and inside the singularity? Is it a portal to another universe, a wormhole to another time, or just an incredibly dense, chaotic knot of quantum strings? Until we can actually bridge that gap in our physics, the interior of a black hole will remain the universe's absolute best-kept secret. I really hope this explainer helped you visualize the terrifying yet beautiful physics at play in the dark corners of space. Keep looking up, keep asking those big questions, and I'll catch you next time as we continue to unpack the mysteries of our universe.